A star inside our own galaxy released a signal that looked impossible. The signal matched bursts usually seen coming from billions of light-years away, but this one was close. If it came from where we think it did, then one of our most trusted explanations for cosmic signals may be wrong. For years, scientists believed these powerful cosmic signals came from only one kind of place. They appeared suddenly, lasted just milliseconds, and released more energy than the sun produces in days. Because of that intensity, researchers concluded they had to come from extremely distant galaxies, places so far away that only the most violent events could be detected at all. This explanation worked. Every new detection seemed to confirm it. The farther away the signal, the more extreme its energy appeared. But then, something changed. In one observation, instruments detected a burst with the same signature, the same speed, the same sharp spike, the same structure. Yet its apparent origin was not billions of light-years away. It was inside our own galaxy. That creates a serious problem. If a nearby object can produce a signal this strong, then either the distant signals are not what we think they are, or the physics behind them works very differently than we assumed. And that forces scientists to reconsider a basic question. Are we misunderstanding the source or the scale of some of the most powerful signals in the universe? The object responsible for this signal belongs to one of the most extreme categories of stars known to science. It forms after a massive star collapses under its own gravity, crushing matter so tightly that a single teaspoon would weigh billions of tons. These objects spin rapidly and possess magnetic fields trillions of times stronger than Earth's. Scientists call them magnetars. Despite their violence, magnetars are not mysterious in the way this signal was. Their behavior is chaotic, but familiar. They release sudden bursts of energy, mostly in the form of X-rays and gamma rays. These outbursts are intense but short-lived, and they follow patterns that have been studied for decades. Importantly, magnetars were never considered capable of producing the specific kind of radio burst that sparked this mystery. Those bursts, extremely fast, sharply defined, and extraordinarily powerful, were thought to come from far outside our galaxy. Their distance was part of the explanation. The farther away the source, the more energy it would need to be detected at all. Magnetars inside the Milky Way simply didn't fit that picture. They were too close. Their emissions, while violent, were assumed to be fundamentally different, lower in radio energy, broader in structure, and easier to classify. So for years, the separation was clear. Nearby magnetars behaved one way, and whatever produced those distant, ultra-fast radio signals was assumed to be something else entirely. In April of 2020, multiple instruments detected a sudden burst of radio energy, unlike anything previously recorded from within our galaxy. It lasted just a fraction of a second, but in that brief moment, it carried a signature that immediately stood out. The burst was extremely sharp, tightly structured, and concentrated in radio frequencies, the same defining traits seen in the mysterious signals that had been arriving from distant galaxies for years. At first, this didn't make sense. The signal wasn't weak or smeared by distance. It wasn't stretched or distorted the way nearby emissions usually are. Instead, it was clean, almost identical in form to the bursts believed to come from billions of light-years away. When researchers traced its origin, the result was unexpected but clear. The source was not a distant galaxy. It was a magnetar located inside the Milky Way. That single detail changed everything. Because if a nearby magnetar could produce a burst with the same structure as those distant signals, then distance alone could no longer explain their power. The assumption that only extreme, faraway events could generate such radio flashes was suddenly unstable. Even more unsettling was what followed. The burst was not a one-off anomaly created by malfunction or coincidence. Its properties aligned too closely with known patterns. The timing, frequency range, and energy profile all matched what scientists had cataloged from extragalactic bursts. For the first time, a direct link had formed between a familiar object inside our galaxy and one of the most puzzling phenomena in modern astronomy. And no existing model fully explained how that link could exist. Once the connection between magnetars and these powerful radio bursts became undeniable, scientists moved quickly to explain it. The first idea was simple. If magnetars could sometimes release enormous amounts of magnetic energy, perhaps those rare events were responsible for the strongest radio signals ever observed. In theory, this made sense. Magnetars are known for sudden magnetic fractures, violent rearrangements of their magnetic fields that release energy almost instantly. If even a small portion of that energy were converted into radio waves, it could produce a brief but intense signal. But the details didn't cooperate. The structure of the burst was too clean. Most magnetar emissions are messy. They spread across frequencies, overlap in time, and fade unevenly. This signal, however, was sharply defined and narrowly focused, more organized than expected from a chaotic magnetic event. Another explanation suggested the environment around the star might be doing the work. Perhaps the radio burst wasn't produced directly by the magnetar itself, but by its interaction with surrounding plasma, charged particles trapped in extreme magnetic fields. Under the right conditions, those particles could amplify and reshape outgoing energy into a clean radio flash. This idea solved part of the puzzle, but it introduced a new one. If environments like this were common around magnetars, then similar bursts should be observed more frequently inside our own galaxy. They aren't. The vast majority of powerful radio bursts still appear to come from far beyond the Milky Way. Some researchers proposed that this event might represent a rare transitional state, a brief phase in a magnetar's life when conditions align perfectly. That explanation explains the rarity, but not the consistency. Distant bursts repeat. Some sources emit multiple signals over time with nearly identical properties. For a transitional phase to produce that behavior, it would need to last far longer than models allow. There is also a deeper problem underlying all of these ideas. If magnetars can produce bursts that look identical whether they are nearby or billions of light-years away, then distance is no longer a reliable guide to understanding their power. That undermines how scientists estimate energy, scale, and frequency across the universe. In other words, this single observation doesn't just challenge one theory. It weakens the framework used to interpret an entire class of cosmic signals. What makes this discovery so unsettling is not that it answered a question, but that it erased a boundary scientists once relied on. For years, distance helped separate the familiar from the extreme. Nearby objects behaved one way, distant galaxies behaved another. That separation no longer holds. If a magnetar inside our own galaxy can produce a burst that mirrors signals seen across the universe, then scientists are left with two possibilities. Either these bursts are far more common than we believed, quietly happening nearby without being detected, or the distant signals are not as distant or as powerful as we assumed. Both possibilities are uncomfortable. One suggests we've been missing events in our own cosmic neighborhood. The other suggests we may be misjudging the scale of some of the universe's most dramatic phenomena. Even now, years after that first observation, there is no single explanation that fits every case. Some bursts repeat, others don't. Some appear linked to magnetars. Others resist classification entirely. What's becoming clear is that these signals are not the product of a single cause. They may represent an entire category of cosmic behavior that we are only beginning to recognize. And if that's true, then this magnetar wasn't an exception. It was a warning that the universe is still capable of surprising us in ways our models aren't ready for. This is one of many unresolved cosmic mysteries scientists are still working to understand, and this channel exists to explore them, carefully, honestly, and without easy answers.